All this other writing that I have on the edges of this slide, you don't have to know. You just need to know, here's the diagram right here. Okay, this is what we just drew out. That's the buffer diagram that I'm referring to. But this is just, I wanted to walk through it so that you see how it responds when we add a base or when we add acid, which portion of the buffer responds and reacts with that to create something that will not affect pH. And that's how it maintains pH or resists changes in pH. Okay. God, you guys have no idea how many times when I'm walking through these lectures I want to be like, any questions? But obviously it's a video, so you can't ask questions. But hopefully you're writing them down and you can email them to me, or we can set up a Google Meet if you want to talk about any questions you do have. Please do that. Okay, let's continue. Now that I've introduced the buffer diagram, let's pretend we have this buffer right here. This buffer is acetic acid, and here's the conjugate base. So let's walk through some scenarios to kind of reinforce our understanding of our buffer diagram and how buffers work. Let's look at this first question right here. Question number 1, what happens to pH if we add NaOH to water? So here we don't have a buffer, here we just have water. So what are we working with? Let's write out a reaction for that. NaOH plus water. What's it going to do? This is our base. So therefore water is playing the role of an acid here. Remember, water kind of will get told what to do depending on who's around it. This is a strong base. So the water is going to donate a hydrogen to OH minus, and it's going to make more water. And then what's left over from water when it donates the acid, or donates the hydrogen ion, OH minus is left over. So this is what we'll create if we have NaOH and water. And this right here, OH minus, it's a very basic substance. The more of OH minus we have, the higher pH. So this will affect pH drastically. Okay, there's no buffer in place to react with the OH minus. So pH will raise, can't spell I-S-E, will raise. pH goes up, becomes more basic. Alright, question number 2 though. What happens to pH if we now add NaOH to the above reaction, this one right here, our buffer, at equilibrium? So when we have a buffer system at equilibrium, what happens? Well, if we look at our handy dandy buffer diagram over here, it tells us we are adding a base, OH minus. The weak acid, which is acetic acid, is going to react with that, and it's going to create water. So which one's acetic acid? Acetic acid is right here. So we're going to have CH3COOH. I'm just writing out a reaction to see what's going to happen. So this is the weak acid plus NaOH. This is our base. And it's the OH minus part that, remember, sodium is just a spectator ion here. These are going to react. I'm gonna actually box this in black. This is our acidic hydrogen on acetic acid. So OH minus is going to grab up that hydrogen. What are they going to make? It's going to make water. Okay. And then what's going to be left over from acetic acid after it donates its hydrogen to OH minus? We'll also have CH3COO minus. Okay. Remember, when you add a base, you make water and you make more of the conjugate base. And this is the conjugate base. So what happens if we add NaOH to the above reaction? Well, what happens to pH? Nothing. Because we create substances, species that will not affect pH. Water and the conjugate base will not affect pH. Okay, what happens to pH if we add HCl to this acetic acid buffer system? Well, we know HCl, if we look at the buffer diagram up here, HCl will dissociate into H plus and Cl minus. And the arrows show us that the conjugate base is going to join up with the H plus, see these two lines coming together, and make more of the weak acid. That's how it will respond. It'll scoop up the H plus from HCl and make more weak acid. So we're going to have the conjugate base, acetate, plus HCl, and that is going to make HC. Let me write acetic acid better. CH3COOH, there's acetic acid. And we'll have Cl minus left over. Okay, neither the weak acid or Cl minus will affect pH, so again, nothing happens to pH here. It is, all the acid is neutralized. And in question 2, this was question 3, in question 2, all the base was neutralized. Okay, if you have questions on any of these scenarios that we just talked about from buffers, please write them down. Please email me. I'm more than happy to follow up with any of you guys. Like I said, you need to be able to walk through this diagram that we drew up here and figure out how a buffer system would respond, what would happen to pH, what we would create, what would be used up, things like that, if we added an acid or a base to a buffer system. All right. The last big topic on buffers is that if buffers, the whole purpose of them is to maintain pH, then we need to know what the pH of a buffer is. Okay? So we're going to now figure out how to find the pH of a buffer system using an equation that you will need to memorize because it will not be given to you on the exam. And we call that the Henderson-Hasselbalch equation. So we'll get there in just a second, but let's read the first statement on this slide. It says we can find the pH of a buffer solution if we know the concentrations of two things, the weak acid and the conjugate base. Okay? If we know the concentration of the weak acid and the conjugate base, we can find the pH of a buffer. So remember, here is our dissociation reaction for a weak acid, HA, in water, and this is the conjugate base. So if we know the concentration of HA, the weak acid, and we know the concentration of A minus, the conjugate base, we can find the pH of our buffer solution. Now for this weak acid reaction, we can write a Ka value. Okay, we've actually already talked about that in some earlier videos. Remember, we do products, concentration of products over reactants, but we don't include water. So we've taken water out, and now we have Ka equals the concentration of hydronium ion plus A minus, the conjugate base, over the concentration of weak acid. Well, if we do some magic on this equation, I'm not going to walk you through how do we derive the Henderson-Hasselbalch equation. I'm not going to ask you to do that on the exam. You don't need to know that. I'm just going to say if we do some math magic on it, we end up with this equation. pH equals pKa plus the log of, here's the concentration of the conjugate base over the concentration of the weak acid. And we call this the Henderson-Hasselbalch equation. You need to memorize this, you need to know it, you need to be able to write it, you need to be able to use it. Okay? All right. And again, you're not going to use this equation to find pH of any solution. We only use, I'm going to abbreviate, the Henderson-Hasselbalch equation to find pH of buffers, not other solutions. Okay, we have a different pH equation for that. pH equals the negative log of H plus. All right. So for any solution that's not a buffer, you'll use this pH equation, but for any solution that is a buffer, you'll use Henderson-Hasselbalch. So we have two equations now for solving for pH, and you need to know when to use